Hey everyone, welcome back to another video by Camroom 5. In this video we're going to talk about carboxylic acids starting off from the resonance. Look at this carboxylic acid molecule where I'm showing the lone pairs and the partial charges of all the atoms in the functional group. What actually happens is that the carbonyl oxygen atom breaks the pi bond with the carbon atom, making it positive. At that exact moment, the OH oxygen atom gives a lone pair to the carbon atom and creates a new pi bond. This creates a slightly different structure which repeats the same pattern, breaking the pi bond and the other oxygen atom giving a lone pair to make a new pi bond. You might ask, why is this happening, or what's the point of it? The point is that these two forms are reversible and you can call them two resonance forms. So a resonance structure of carboxylic acid exists where the oxygen atom of carbonyl group and the oxygen atom of the OH group are constantly making and breaking the pi bond with the carbon atom. So you can see the red oxygen atom and the blue oxygen atom with their lone pairs, and you can also notice that the pi bond is never localized, it's always delocalized with the negative charge spread on both the oxygen atoms. And the hydrogen atom is not exactly bonded to a single atom, it's bonded to the resonance. So you can see that there is a delocalization of pi electrons on the carboxylic functional group. That is why it easily dissociates and releases the H+. Now I want you to look at these three carboxylic acid molecules. On the left hand side, you can see that there's an acid molecule A, then B, and then C. How are they different? You can see that on the acid molecule A, there's an alkyl group which is ethyl group. In acid molecule B, you can see there's an electronegative chlorine atom attached on the second carbon. And then you can see in the acid molecule C, there are two chlorine atoms attached on the second carbon from the carboxylic group. If you compare their acidities, acid molecule C is going to be the most acidic functional group acid with the highest Ka value, it dissociates the most, and it has the smallest pKa value. Acid molecule A, on the other hand, is the weakest acid and it has the lowest Ka value among all three. It dissociates the least and it has the largest pKa value. Why would the presence or absence of chlorine change the acidic nature of these acids? So let's have a conversation about that. What actually happens is that chlorine atoms show their electronegativity and the alkyl groups show their positive inductive effect. So our groups have the positive inductive effect. What happens because of that? Actually, because of the positive inductive effect, the electron density on the carbon atom in the carboxylic acid group, obviously, so the electron density on the carbon atom is increased. And what happens? Because of that, the OH bond is not weakened at all. Because the carboxylic functional group receives a lot of electrons from the alkyl group, so the OH bond is not weakened, it doesn't break. But when electronegative chlorine atoms are present in the acid, they show negative inductive effect. What's negative inductive effect? That is electron withdrawing effect. So the electron density on the carbon atom of the carboxylic group is decreased because the chlorine atom withdraws electrons, and as a result the OH bonds are also weakened and now they break down and dissociate. Let's compare this carboxylic acid molecule which has two chlorine atoms attached to it. What actually happens is that once these kind of acids dissociate and they release their H plus ions, which is also known as the proton. Because of the electron withdrawing effect, the negative charge on oxygen atom is more delocalized because there are electronegative atoms pulling it. So the negative charge is delocalized due to the electronegative chlorine atoms which are present as part of the acid molecule. This is also known as the negative inductive effect. So it helps in the delocalization of the negative charge and it makes the carboxylate ion more stable. The carboxylate ion, which is the carboxylate anion, is more stable. Is stabilized, I can say that. And as a result, the equilibrium shifts towards the right. The equilibrium moves or shifts towards the right, which means more dissociation happens, more H plus ions will be released. So acid molecules with more electronegative atoms dissociate more. Compare these 4 acid molecules. Each time I am adding one more chlorine atom on the second carbon. You can see their Ka values at 25 degrees Celsius. With more and more electronegative atoms, more negative inductive effect is seen. So more electronegative atoms, negative inductive effect is seen, is observed. So that is number 1 point. You can say that less electron density on the carbon atom because of the electronegative atoms, right? And the OH bond is weakened, and when the OH bond is weakened, it's going to break down, it's going to release the H plus ions. You can also say that the carboxylate ion that you make after their dissociation is more stabilized. So these are the 2 arguments that you can put forward to talk about the acidity. So when there are more electronegative atoms, you can talk about the weakening of the OH bond, and then you can also talk about the carboxylate ion is more stable because of the extension of the delocalization on COO minus ion. So the bottommost acid is the strongest acid and it has the most stable carboxylate ion because it can delocalize more because of the electronegative atoms. The topmost one is the weakest acid and it has the least stable carboxylate ion because the negative charge can't be delocalized since there are no electronegative atoms. So you can see the topmost acid has the smallest Ka, which means it's a very weak acid, but the bottommost one has the largest Ka, which means it's comparatively the stronger among the 4 acids. Let's talk about the oxidation of the carboxylic acids because that's another topic that can be asked us. The oxidizable carboxylic acids are only 2. One is methanoic acid. Because of its aldehyde group, methanoic acid can be oxidized. The second is a dicarboxylic acid, particularly the ethane dioic acid, which is also known as the oxalic acid. So let's have a conversation about methanoic acid and its oxidation. Methanoic acid can be oxidized because of the presence of the aldehyde group it has. It is oxidized to form carbon dioxide and it loses 2 electrons. You can also write this equation showing oxygen in square bracket where carbon dioxide and water molecule is formed. What are the oxidizing agents in this case? So if you remember AS level chemistry, you would remember that methanoic acid can be oxidized using two compounds. If I take methanoic acid sample in test tubes, there are two chemicals which can help to oxidize it. One is the Fehling solution, which has copper 2 ions in it, and the other is the Tollens reagent, which has the silver plus 1 ions on it. If you heat them, so Fehling solution gives you brick red precipitates and Tollens reagent gives you a silver mirror. So Fehling solution gives you brick red precipitates of copper 1 oxide, and Tollens reagent gives you a silver mirror. This happens when the Ag1 ions are reduced to form Ag. Ethane dioic acid or the oxalic acid is the second carboxylic acid which can be oxidized. Oxalate ions, or you can say oxalic acid, can be oxidized using acidified manganate 7, where you receive carbon dioxide and obviously manganese 2 ions. This equation is not balanced right now. Based on the oxidation number, you can see that the carbon oxidation number changes from +3 to +4, which means it's oxidized. So the carbon atoms are oxidized, and the manganese atoms are reduced because their oxidation number changes from +7 towards +2. The whole idea is that these two acids can be oxidized. In the next video, we'll talk something about acyl chlorides. Stay tuned, guys. Thanks.